In this tutorial, we're going to introduce classes for Python. We can open up either a blank file in both Rhino and Grasshopper, or if you would like, you can use the example file, which is day02_Python class. We have these example components to the left here, but like in previous tutorials, I'll be building these components again from scratch. So first, an introduction to classes. Classes in Python may seem to resemble earlier coding structures like functions. However, they offer a unique ability to pair data with functions all nested inside of a particular instance. So when we build a class, we can instantiate an instance or an object of that class, which contains its own data and function. This means that we can create multiple instances of each class, allowing us to access independent data histories and functionality for each of these instances. This may make more sense once we get into the code. So the first thing we can do, like always, is double click in our Grasshopper canvas, type GH_Python, and open up a new component here. In this case, we only need one input and one output. So I'm going to zoom in and just select minus so we can delete those outputs. And then if we want to, we can right click on Python and name this message class. You'll notice that I removed the A and not the out. This is because the out, it says the execution information as output and error streams. So when we're in the Python script editor and we hit test and we see the printouts, it actually sends it out through this out parameter. If we right click on message class, we can see that we have a show code input parameter. We also have a show output out parameter. So that show output out is what allows us to read those printouts outside of our Python component. In order to read that and make it more visible to us in the Grasshopper window, we can double click and type channel, and this will just make it easier to read those printouts as we go. Now our input, I'm gonna just add an underscore, type IN, and we can jump into the component. So the first thing we want to do to build a class is type class space the name of our class. In this case, I'm going to just label it message and then colon, enter, and now we're inside of this class. I'm going to make a variable here called message and set this equal to hello world. Now, if we hit test, we can see that nothing's happening. This would be similar, if it's easier to imagine, to defining a function but not actually calling it. So we've started defining some aspects of the class, but we haven't actually created or constructed an instance of this class object. If we want this class to do something, not only do we need to call it, but we can also embed a function inside of it. So we do this very similarly to functions outside of classes by saying def, and then we can make this function any name that we want. So def message, and then similar to other functions, we need an open parentheses, but a unique aspect of classes is that we need the first input to reference the class itself. So each of the functions inside of a class need to know that they're inside of a class and passing the data from the class into each of the functions. So we need to write self and then comma, and then any input parameters here in this print message, which for now, we don't need any, so we can close the parentheses, hit colon, and enter. Now, anything inside of this function, so any functionality we want to add, we can add into this tabbed portion. So in this case, I'm going to say print, and let's say print message. We have print message. I'm going to just demonstrate constructing this class. To actually call this, or what's called construct this class instance, we need to set a variable. So this will be my message. Then we can set this equal to the class. So here we're calling that or instantiating that, setting it equal to my message. So if we hit test, nothing is happening. We're only running this instantiation. So we're not actually running the function inside of this class. We're just creating one instance called my message. If I hit print my message and then hit test, we can see that it is a main message instance. So this is an instance of the class message. If we want to run the function inside of it, we now need to call my message, then dot, and the name of the function, message, which takes no inputs. So we can now hit test. So now it is running that function, but we're getting an error on line 11 in print message. Global name message is not defined. This is because the whole reason for passing self into each of these functions is that we need to refer to the class itself to grab the data from elsewhere in the class. So if I type self.message, hit test, we can see that it now prints hello world. That's because it knows it is the variable or class property message inside of the instance itself, this class itself. In this case, we don't actually have an init or a constructor function, and this will still work. We can see that it's still printing hello world, but if we wanted to pass something into this, let's say we wanted to feed in a string from our input parameter here inside of Grasshopper. So we want to feed in _in, and then if we hit test, this constructor takes no arguments. So what we need to do to fix this is we actually need to go under the class, tabbed in one space, and type def. And then this is particular syntax for classes. It's just best to kind of memorize this. If you have any questions about it, I can answer those separately. But we'll write underscore underscore init for init, and then underscore underscore, open parentheses. We need to feed in itself like in every single function under a class, and then any input parameters. So in this case, I'm going to set this to message and set message equals message. Now we need to tab in message. Now if we hit test right now, we can see that message instance has no attribute message. So it worked to just have message outside of an init function, but once it gets placed inside of this constructor, we now need to add the self.message so that it knows it's referring to itself, the property message inside of this class. So if we hit test, we can see that it's now printing none. That's because we have no input parameter. If we double click inside of Grasshopper, plug that into the in, it's now printing this message. Double click to edit, you can say king ... and we now see that this message is printing. So now that we have a class that is working and printing, if we minimize the class, we've referred to this once, but one of the nice things about classes is that we can actually refer to it multiple times, feeding in different data inputs, but using the same functionality. So I can now make a second instantiation of this class. So my message2 equals all the function message, and instead of in, we're going to feed in world. Now we need to say my message2 and then dot print. Now we see it print the first my message printing, and then the second hello world. So I'm going to hit OK there, and we can move on to the next example. So in this example, we're going to make another GH-Python script. Now we just need a point input, and we need a point output, and we can say double click to open it. Up at the top, we're going to need to import the Rhino script syntax as rs, as well as script context sc, and I think that should be it, but we may need some others later. And just to make sure we are in the Grasshopper document, let's just type sc.doc equals gh doc, enter, enter. And now let's build a class. I'm going to call this class point, and we can create a constructor function. And in this constructor, we need to feed in our input point. So in this case, I'm going to call this underscore pt, close parentheses, colon, enter. Now, inside of here, we actually want to refer to this as the location of the point in class point. So I'm going to say self.loc for location equals, and we're going to set this equal to the variable that we feed into this class. Now, if we call this by saying my point equals, we can see it does need that input parameter, so we need to feed in point. That now satisfies that, and we just need to inside of Grasshopper. So right now that's just a point at the origin. We hit test, we get no errors. Inside of the init, if we type print self.loc, we can see that there's a GUID reference there to the point we've just constructed inside of Grasshopper and fed into the underscore point. So similar to Python and Grasshopper exercises, we're going to look at how to move this point along one particular axis, and then create a series of points that make a line in that axis. So in order to do this, we're going to need to add some functionality to this class. So we can do that by adding another function, and I'm going to call it def.move. I'm going to feed in self. Now, if we want to run this once, move it 1 unit in the x direction, then we would want to say point equals self.loc, so the current location of that point, and plus 8 vector, and say 1, 0, 0 to move it 1 unit in the x direction. We now need to call that function, so my point dot run move, and hit test. So we can see here that we actually get an error. This is a pretty common one, and there are 2 ways to fix this. So this is because the discrepancy is between geometry objects and the GUID references. So right now it's saying GUID and vector3d cannot be added, which we've added them there. If in the init we actually just type rs.coerce 3d point, this will make sure to change that GUID input into an actual point geometry. And now when we hit test, we don't get that error. Another way to solve this is actually to change it as a type hint in the input parameter in Grasshopper. So if you just right click on point, go down to type hint, and find point3d, you'll know that we're feeding in point3d into the Python script editor. Now we want to find a way to output this point, because right now our point is set to 0, 0, 0, which was the input point. If we don't want to confuse those, we can say out maybe. So now we should see that. Hit test again as null. So if we make a new variable point out and set this equal to my point, then we actually want to, similar to how we call functions inside of classes, we want to actually grab this property location, so myPoint.loc, and this will give us whatever current location after running the run move function. So when we hit test, one more thing that we need to do is, instead of new point, in this case we need to set self.loc to that new point because we're actually going to update the location parameter based on function. So when we hit test, we can see that it has now made another point 1 unit forward on the x-axis. So like we did in both Python and Grasshopper, the next question is how would we do 10 of these? There are actually a few ways to do this, but the first way I'm going to show is just adjusting the function inside of the class, which may seem more familiar based on previous exercises. So we've done the move once, but if we wanted to still only call the run move function once and loop through this transformation 10 times, we can use a loop. So for I, instead of this, we could just say set x to I so that I is going to loop through values. We could just call this for x in range and then set this to x. But instead of a vector, we want to keep this as a point. So create point. Now this will create a point at 0, 0, 0, 1, 1, 0, 0, and so on. If we hit test though, we can just see that we just end with the last one, which would be 9, 0, 0. So we want to find a way of actually storing all of the steps in between the beginning and this end step. We can do this by creating a list property called self.history, and we can set this to a blank list because we don't have history once we start. Oftentimes in the init, once we've constructed a list like this, we may append all current positions to it because our functions will likely change it. But in this case, we don't need to. So we just need to make sure that after we run this transformation each time, we append our self.location. So self.loc_history.append. So we're appending our current location to our list of history points. Now, instead of making point out, we can say points out, and we can say my point dot loc history. And we see that we have 10 point outputs from 0, 0, 0 to 9, 0, 0. We could do this as well with a nested loop. So for y in range 10 or 10, and then we could tab those in and say y, z, test, get a 3D array. So for the next piece, we're actually going to work on converting just the singular, the one-dimensional list. So this list of points into a line that moves through them, or a polyline moving through all of these points. Now I'm going to change the name in the init function to trail points. We're going to change each instance of loc_history into trail points now that we're drawing the trail through them. So these are going to be the points that we then draw the polyline through. So we can make a separate function called def_render_curve, then self. And what we're going to want to do is run each of the moves, store that list of all of the trail points, and then call this function render_curve. So after run move, we're going to call the function myPoint.render_curve. And then inside of here, we want to say return so that we can return something out of this function call. So return space rs.add invert, or if we wanted to first start with a polyline, we could say add polyline. Then we're going to feed in here self.trail points. Now if we hit test, we see that there's nothing being output. We still have these points set, but nothing is actually coming out of this. We just need to set a variable here to get this item being returned. So if we set this to trail, and then set this output parameter to trail as well, and hit test. It's a bit difficult to see because it's on the axis there, but we are rendering that trail or polyline curve through those points. To make it a bit easier to see, we could just say, make a diagonal set of points. Now we can see that curve being drawn into space. One of the cool things about not just classes, but also functions and being able to draw using X, Y, and Z coordinates like this is that we can actually construct curves entirely through mathematical operations. So I'm going to create an adjusted version of this run move. This way we have something a bit more exciting than this diagonal polyline there, which could be just reduced down to a single line. So we're going to make def run math in self. Now in this case, what we want is we actually want a nested loop through a u and then a v, so for u in range. And these are going to work with trigonometric functions. So this range is going to relate to the range of the trigonometric function. So in this case, I'll use 360, and then for v in range 60. So now we have our nested loop. The next thing we want to do is actually translate these 360s, which is in degrees, into radians. So to do this, we need to go up to the top and import library, and then say UR, so U radians equals U math.pi divided by 180. Now we can do the same thing for EV. And then the next thing to do is just to set the X, Y, and Z values. And then we're going to do something similar to the run function. So self.loc equals, and we're going to have a create point, and then we also want to append these to our trail. So self.trailPoints append self.loc. So this is going to be very similar, and then here we just want X, Y, and Z. So I'm actually going to use a set that is presented, and this is one example from Joseph Choma, a former professor of mine, who operates with mathematical transformations to render curves and surfaces. He is extremely talented working with these mathematical transformations. He actually has a book out called Morphing, a guide to mathematical transformations for architects and designers. And this is one of the transformational examples in this book. So if we just copy these in here as the X, Y, and Z values, then we just need to adjust a bit of the syntax. So we're going to use UR instead of U radians, R instead of V radians. Now we could use simpler equations. Feel free to experiment with these, it will work. But if we run this one, we can see we get pretty complex transformations just through drawing curves through a series of points. So this is a kind of twisted torus. If we change the domain of the nested loops, so we can do 180, the V value at 360, and we get a kind of half-twisted torus. We can change any of these parameters, so let's change this from 10 to 20. And we can see the form starting to slightly shift. So even doing something like nesting all of this, since we see it's essentially an upside down fault, we could say -1 times that, and it now flips it right side up. We can even say it's maybe down 10 units. So if we just say